is Gaurav Katoch from IIT Hyderabad, and he will be talking about quantum complexity and bulk time-like singularities. So, yeah, over to you, Gaurav.
Yeah. So first of all, I would like to extend my thanks to Chetan for inviting me to present my work in this talk, and Srijan to seamlessly coordinate with me in the meantime. So this talk is based upon our recent work, which is concluded in collaboration with my supervisor Shubho Roy at IIT Hyderabad, and this G Ren from Sun Yat-sen University at China. So in this work, we turn our attention towards the naked time-like singularities with the hope that the complexity might have something novel to tell us about them. So here is a rough outline of my talk. So first of all, I will introduce the notion of computational complexity. Then I will present it some holographic proposals. Further, I will discuss some universal features of complexity of space-like cosmological singularities, followed by a look at a warm-up example of a negative mass Schwarzschild ADS, that is negative mass ADS black hole. And then we will look at some more realistic example of a time-like singularity which arises in a Kasner space-time. And further, we'll go ahead and follow up with the complexity characteristics of a time-like singularity which arises in the Einstein scalar system. And finally, I'll conclude. Sorry. So the quantity we are interested in today is not entanglement entropy, but some extension of it, called the notion of computational complexity of a conformal field theory state. It's not a usual kind of observable that we talk about in the quantum field theory, because in quantum field theory, we are usually interested in the quantities which are independent of the regulator scale or cutoff. But it turns out that this is some quantity which is like entanglement entropy, in which we can never get rid of a regulator. So the computational complexity. So this idea is borrowed from computer science literature, and it quantifies the difficulty of performing a computational task. The definition is a bit qualitative, and in order to make it precise, we need a few ingredients. So the ingredients which go into defining the complexity are, first of all, we need a system, a set of states, a reference state, a target state psi, a set of simple k-local operations, which take us from one state to the another. So the notion of k-local is that these simple operations are also called gates, and they act upon k qubits at a time. So that's why they're called the k-local gates. And the complexity of a state psi relative to some reference state O is the minimum number of simple operations which are applied to the reference state in order to get to the target state psi. So, and the complexity in the quantum setup is, it just gives you, it quantifies the difficulty of preparing that quantum state. So what happens is that classically, if you look at a system with, let us say, you have n classical spins or classical bits, and then I could take a reference state in O in which all the spins are, for example, in which all of them are uniformly aligned. And then I can ask about a target state which has some subset of m spins out of those n are flipped. And we can ask, like, what is the complexity of that target state? The answer would simply be n, because you have to flip those. The simple operations will just be spins, and you have to flip those m spins. And therefore the answer will simply be m, and this is also this will also, the m is also the entropy of that system, because you have 2 to the m states, and you take 2 to the m, the log of 2 to the m, and that gives you your entropy also scales like m. So we see classically that there is no difference between the complexity and the entropy. Both scale linearly with the degrees of freedom of a system, that is the n here. Therefore, we see we don't have to invent this concept of complexity in the classical systems, because the entropy is good enough to capture the complexity of a classical state. But however, the whole game changes drastically as we bring quantum mechanics into picture. So now, again, the entropy still scales linearly with the number of degrees of freedom. But here we see, due to the due to this principle of quantum superposition, we now, instead of m binary digits, we now require these 2 to the n alpha i's. So these are the coefficients, and i's are a typical this eigencats. So you have 2 to the n eigencats, and alpha is are 2 to the n tunable complex numbers. So you see that quantum complexity now it scales, it scales exponentially with them. So, so this tells us that complexity is really a new concept, and it captures this feature of quantum mechanics, which entanglement entropy fails to capture. So you can interrupt me anytime, if I'm not clear in my yeah. So yeah, here is a diagram that depicts the characteristic of complexity and its conjectured growth rate for a typical quantum mechanical system. A typical system evolves. So it what happens that as it evolves, the quantum mechanical system I'm talking about, it thermalizes way too early when entropy becomes proportional to the degrees of freedom. And this happens within a polynomial time in the number of degrees of freedom. But what happens is that the subtle changes keeps happening in the system, and its complexity keeps growing at a linear rate until it attains this exponential value in this exponential time, and it saturates there. The system, the thing is that the system still evolves uh, in some manner, and complexity still keeps increasing when it is in this part of the curve, uh, way beyond the thermal equilibrium. And it grows till, like I said, it reaches this value, and it spends a big number of time there, a long number of time. It stays there because because of the availability of a huge number of highly complex states. But we are, however, interested in the region of the conjectured linear growth of the complexity given by this rate equation. So the formula for the growth rate comes from a very educated guess. First of all, because complexity is an extensive quantity, so its growth rate must be proportional to the number of active number of degrees of freedom. Therefore, it is assumed to be proportional to the entropy, the thermal entropy of the system. Secondly, since complexity just counts the difficulty or the number of gates, so it's just a number. So in order to match the dimension, this is 1 upon t, it has the right hand side has to have the dimension of energy. Therefore, we multiply it by this temperature here in order to, make it dimensionally correct on the left hand side and the right hand side. So, right. So at this point, now I implore you to look at a different bulk feature, which looks very disparate from at the surface level from what we were discussing earlier. So what you see here is a Penrose diagram of an eternal ADS black hole, which has a dual interpretation of being given by the thermally entangled CFT, which live in this left and the right boundaries. So here is a horizon of this black hole, and the region of the green curve passing behind the horizon, seen here in green, is called the Einstein-Rosen bridge or the wormhole. And it has been known for a long time that this ERB volume or this wormhole's volume, it keeps growing forever, even past the time scales after which this black hole thermalizes. So, and the growth rate of this ERB is also captured by this linear is it is also linear in the boundary time. So the time runs upwards. So as you go up, so it linearly increases with time. And now we know that that in the ADS CFT duality, which furnishes us with a non-perturbative definition of quantum gravity in the asymptotically ADS spacetimes, in terms of the boundary field theory that lives in its conformal boundary, it supplies us with a holographic dictionary that allows us to make contact between the bulk and the boundary quantities. So now in the light of the ADS CFT duality, there arises a natural question as to what CFT feature encodes this ERB growth. So this characteristic growth rate gives the supporting argument which lets us kind to conjecture that the holographic duality of to conjecture the holographic duality between the Einstein-Rosen bridge volume and the complexity quantum computational complexity of a dual boundary theory state. So this like again this supporting argument also comes from looking at this equation, which also claims that the rate of growth of ERB volume is also proportional to the black hole mass. So that can only be obtained if you have this careful choice of these coefficients, these constants here. So this gives us what is called a complexity volume conjecture. So it is conjectured by Susskind, who conjectured that irrespective of the way we define complexity in the quantum field theory, the complexity of a boundary state is given by a maximal volume slice through the bulk, which is anchored at the time at which this boundary state is defined, like in these two conformal boundaries, and modulo the overall constants which are present here for the dimension reasons, because this is the volume for dimension one slice, and gn goes like d minus 2 in the length. So like this has dimension of l to the capital D minus 1, and this overall has a dimension of l to d minus 1, thereby making it dimensionless quantity. But the thing is, this L is a characteristic length scale, which is like it is specific to the geometry. We'll come to that later. And there's also any question by this time? All right, I'll move ahead. So Susskind also conjectured that irrespective of the way define complexity of sorry, yeah, sure. So that was and this is also true for this case. So there is also an alternative formulation here due to Susskind, which furnishes us with a more universal looking formula. And this is given in terms of this IWDW, which is a gravitational action, which is evaluated over this something called a Wheeler-DeWitt patch, shown here in this pink lines. It is bounded by these null curves, the region inside here. and uh, and it is evaluated at a Wheeler-DeWitt patch, which is anchored at the appropriate boundary times at which that CFT state is given. So what is first? Let's recall that the Wheeler-DeWitt patch is the union of all the space-like slices that joins the field theory states, which are given at these boundary times, including their boundary, including the null curves as well, like which furnishes the boundary of this Wheeler-DeWitt patch. All the space-like curves joining this TL to TR, as well as the null curve, which kind of forms the boundary of this Wheeler-DeWitt patch. So the terms which appear in the gravitational on-shell gravitational action are of these kind. Shown here. The first term you see is the Einstein-Hilbert volume term, which is evaluated in the bulk of this Wheeler-DeWitt patch. And second, this term is the Gibbons-Hawking boundary term, which is evaluated over these null uh, curves here, which are the boundaries, and also this singularity. Like this also forms the boundary of Wheeler-DeWitt patch. It's a space-like. And and together with you have a third term which also gives you the contribution due to these joint terms where these null curves meet these time-like curves, or null curves meeting this the space-like curves here. And yeah, so right, so all these terms are required in our prescription for the action in order to make the action principle diffeomorphism invariant and well defined. But in our work, we instead choose a different prescription scheme, which allows us to evaluate the on-shell gravitational action in one shot without applying, just by applying the Gibbons-Hawking prescription, and without caring about these different null terms and the null joints. So what we do is that we look at this part and we deform this null boundary to a time-like surface, regulating surface, by introduction of this regulator shown in this small here, which is lambda UV. So with this careful choice of this regulator, we deform this null boundary into a time-like boundary, and in the end we use the normal this Gibbons-Hawking York prescription to evaluate that term in or corresponding term in the action, and in the end we get rid of this regulator by to get the full null boundary answer. Right. So yeah. So these are the here I contrast these two prescriptions. So there is an like I said, there's an appearance of an ambiguous, arbitrary characteristic length scale in the CV, which is short for complexity volume, and which is an undesirable feature of a CV, because. But this is not so in the case of CA, because in CA, unlike CV, it has a more universal appeal, because you see there's only the appearance of this universal constants here in the action complexity. And secondly, this CV prescription being a variational problem, it's operationally difficult to solve. In this case, the action formulation is more preferable because it requires the evaluation of just the integrals over that Wheeler-DeWitt patches, and in order to solve for the complexity. And and the way we define complexity here, it works very well for the discrete finite systems. However, for the continuum systems, like in the quantum field theory, the complexity is not a very well defined quantity as the number of degree of freedom diverges, because there sits a degree of freedom at every space-time point, and there's a lot of work going on to come up with any unanimous way uh, of defining the complexity in a quantum field theory, but the work is still far from completion. We have like we still have many boundary prescriptions for formulating the complexity based upon different schemes for choosing the gate set or the target states or the reference states, but none of them agree. uh, you know uh, uh, None of them agree because they do not reproduce the universal divergence pattern which is exhibited by the holographic descriptions. And but in the recent work by Balin, Myers and company, they have shown that there are also many ways of associating the complexity with the geometric structures in the bulk. However, it's also good that the holographic, like I said, they are able to reproduce the leading divergence behavior successfully, but we are still at dark at like how to associate regarding the holographic map between this boundary and the holographic bulk prescription. So we are still at dark about that, like which prescription of choosing or defining the complexity for a for a field theory quantity, like for what field theory definition correspond to what holographic definition. So that map is also not clear at this juncture. So now I'll come to our main body of work. But before that, I will like to pause and would like to take some questions if somebody has something to ask if I'm not clear. Okay, so moving on. Well, the past works on the cosmological singularities have universally demonstrated to us that the complexity monotonically decreases as we approach the naked space-like singularities. And this happens because in the it's very easy to see in the CV prescription, because you have this maximal volume slice, and as you go towards the singularity in this diagram, perhaps, yeah, so as I evolve it up and this maximal volume slice, it tries to go near to the singularity, and but as I go near singularity, there is crunching of a space-time volume element is happening, and that results in the reduction of degrees of freedom. But this slice being by definition a maximum volume slice, so it tends to like repel from the singularity to in order to maintain its maximality. And this loss of complexity as going near the singularity, it is reminiscent of another phenomena, very popular phenomena of the firewall paradox, in which we have seen that the lack of entanglement between the degrees between the late time Hawking radiation and the early time Hawking radiation after the page time. Due to that entanglement and the monogamy of entanglement, there exists a firewall phenomena, which is also a kind of singularity that does not occur in the classical gravity. So this thing, it hints to us that perhaps singularities have a more simpler entanglement structure, and it is natural to extend that investigation for like these cosmological space-like singularities for the case of time-like singularities, and to see if whether this complexity also exhibits such universal signatures which pertains to time-like singularities. So what happens is that such time-like singularities, they arise in the bottom-up effective holographic theories of ADS-CMT systems, and are generally resolved by lifting them to higher dimensions or in the full string theory setup. So they are not singular in the full string theory, but are smoothed out by the inclusion of stringy states or the branes. But that's not always the case with all the time-like singularities. What we would like to know is that if a certain time like singularity which occurs in the semi-classical gravity, is it resolvable or not? So there's no universal mechanism for resolving generic singularities, but Gupser criteria, there's one criteria by the name of Gupser criteria that acts like an effective rule of the thumb approach. It is like a rule of the thumb approach in order to identify an allowed singularity by bypassing the full string theoretic setup. So it just basically says that if a singularity arising in the ADS-CMT systems, it can be realized in the full string theory, then that singularity is kind of allowed. And the naked singularities that emerge in the geometries that can be taken as the limit of as some extremal limits or the deformation of the regular black holes, they are always resolvable in the full string theory. And for example, if we take a regular black hole or take it's on the like in the opposite direction, if we have some regular black hole and we take some extremal limit or some deformation of it, and we end up with the kind of naked singularity, so that naked singularity will be allowed. So and if this is not the case, then those singularities are pathological and they cannot be there in the full string theory. So but this Gupta criteria, it is operationally very difficult to implement because one actually need to discover the full embedding of full embedding without giving any universal prescription or algorithm to do so, like how to go about, like what is the way to find the full embedding of some singularities which occur in the holographic systems. So we therefore turn towards holographic complexity to give us some signature as a diagnostic to treat such singularities containing time-like such geometries containing time-like singularities. Right. So now, first example we want to look at is the negative mass ADS Schwarzschild case, which is not a good system to look at because the CFT has no ground state for a negative mass Schwarzschild, and it can be seen like this is the metric for this system, and here is the blackening function, and this is the mass parameter, and it occurs with the opposite sign. This is time it's a positive sign, but normally for a positive mass black hole with a space-like singularity, you have like you can recall there's a negative sign here. So like I said, this CFT dual CFT states to this geometry is sick because it does not have a ground state. So therefore, this is not allowed by Gupser criteria, and we know this from the beginning. And but we are just treating this as a warm-up example to test the singularity conjectures, which we will come to later. Like, yeah, and yeah, this uh, R equal to 0 is the time-like singularity, is the location of time-like singularity at which your curvature your curvature blows up at that point. So what we did is that first of all we look at the volume complexity. So using the variational approach, we maximize the volume functional using the Euler Lagrange equations with a suitable boundary condition that gives us this following result for the volume complexity. So here lambda occurs as the bulk IR cutoff, which encodes the UV divergence of a boundary field theory, and you see like right mu, like I said, this is a mass parameter, and this is the formula for the action complexity. So uh, these are the divergent pieces. The first piece comes from the Einstein-Hilbert term. This second piece, it comes from the null boundaries, which we deformed to be time-like, but we took the null limit and we obtained this from the boundary of the Wheeler-DeWitt patch. The singularity, sorry, I should say, like that first term comes from evaluating in the CA prescription over this region, that Einstein-Hilbert action. The second term comes from this part, the null boundaries. There is zero contribution coming from the singularity, and as well as these joint pieces here, they also does not contribute. So what happens is that in both of these examples, CV and CA, they both exhibit quadratic UV divergence, which is expected of any local boundary field theory, in which, like in any local boundary field theory, any extensive quantity like complexity is supposed to scale like a spatial volume of the boundary CFT. And therefore, we expect quadratic divergence in 4 dimension when I take capital D to be 4. And both definitions of complexity, they display very weak dependence upon mass parameter, which is evident from the fact that the dependence upon the mass parameter comes from, like, even in this blackening function, you can see the mass parameter, it is suppressed by the UV cutoff when I in the UV in the UV range. If I look at the UV behavior, so this term will be highly suppressed, right? So that does not affect it very much. So the complexity results, which I'm not showing right now, but take my this at the face value, that what when we evaluated that, the complexity result at the first glance, they look very physical, very positive, because complexity is supposed to be a positive, to give you a positive number, counting the number of gates. But so the complexity result doesn't look anything pathological at all in the beginning, at a surface level. But the only indication that perhaps something is wrong with the complexity result is that the complexity for this time-like boundary, or for this time-like singularity case, was less than the empty ADS case. And that is the case opposite to for the positive mass black holes. You always find your complexity of Schwarzschild ADS with the positive mass to be greater than the empty ADS. So we are treating this criterion as perhaps the only indicator which captures the thickness of the geometry, which taken at the face value will just imply that perhaps it's by somehow it's very easier to create an empty ADS than the to, to create the negative mass ADS than the empty ADS, when the complexity of empty mass ADS is very small. This implies some sort of instability in the underlying theory, because how come it be that it's very easy to create a black hole than the empty ADS? So this we set up as a criteria for complexity, and we test it against other examples in the further sections. And so what we see is that action and volume complexities both are consistent with the Gupser criteria. Recall that the Gupser criteria, it rules out this geometry because of the dual boundary CFT being sick. So it is ruled out by Gupser criteria. And this behavior is also registered by the volume complexity as well as the action complexity when we compare it to the complexity of an empty ADS crystal. So this time we tackle more realistic example of an anisotropic geometry which contains this time-like singularity in the bulk. And this appeared in the work of our collaborator in this G. Ren in this work. And this kind of geometry, it arises in the effective holographic theories. Like all we know that the effective holographic theories are of immense importance to the ADS-CMT systems and arise as a result of taking a sequence of limits in which we turn off the stringy physics by taking alpha primes to 0. And we also take the volume of the compactified dimensions to be 0. So this time-like version of yeah. So this time-like version of more familiar, this is the time-like version of more familiar geometry, which is called the space-time space-like Kasner singularity, which occurs as the exact solution to ADS sugar equations. The only difference this time is that this time we have also allowed the time direction to scale, like f to the alpha, where f is given by this number. And we are also allowing this time direction to be time coordinate to be scaling. We are also scaling it like the spatial regions here, x and y. So these exponents, alpha, beta, and gamma, these are called the Kasner exponents. And these are not independent, but are related by a set of two Kasner conditions, thereby making only one of them, which we chose to be alpha here, as the independent exponent. There's only one independent exponent because of two Kasner conditions. And Z naught here is the location of the time-like singularity here. and z equal to 0 is the spatial infinity. So this geometry is obtained by recrotating the space like ADS Kazner, and it cannot be realized as some limit of extremal black hole. But instead, it is obtained by recrotating, like I said, the ADS Kazner in the Poincare chart. And therefore, it doesn't occur in the full string theory. And hence, it is ruled out by the Gupser criteria. And therefore, we expect complexity to display some pathological trait. So if you have any answers, you can interrupt, like I can pause for any answers, any questions at this point. Right. So moving
So,
on. Yeah.
excuse me. So
Yeah.
the last, I mean, the previous example you were looking at, that was some
Hmm.
like naked singularity.
Yeah, it is a naked singularity.
So the next one, that is that has some kind of like some defined structure, or
What
I mean,
has
your
some different structure
sugra.
for this case?
No, no, no. The next example, like
This
this,
one.
yeah.
Okay, Kazner example. So what's the question?
So here you have some kind of, I don't know this what is the structure, but some horizon or some.
Yeah, this is not a horizon because it's a time-like singularities. So you have horizons for the space-like singularities. These are naked singularities. These are time-like. This is like, you have horizon Nordstrom singularities, like, but it's time-like, but they are guarded by those horizons, but it
Yeah,
is not guarded by any horizon. What I showed here is a Wheeler-DeWitt patch. So I have a boundary state anchored at this time, and this is the null boundary of a Wheeler-DeWitt patch. And like this singularity, it also forms one boundary of a Wheeler-DeWitt patch, and this is what I'm showing here. Yeah.
Hello, can I ask you a question?
Yes.
Yeah. So because this singularity is also attached to the like boundary, right? Uh,
Yeah.
so it means like that. Can we also observe this type of singularity in and the boundary theory in time when
No, no,
we
no. No, 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 no. No, that's not true. This line is equal to 0, but it's an artifact of this Penrose compactification. For example, recall your regular Penrose diagram here. You also have r equal to 0 and r equal to infinity, but they seem to be joining here at this point. So this is like exactly same thing happening.
okay, okay, right,
Yeah.
okay.
Yeah.
so your singularity, I mean, this red line is at z equal to like,
Yeah,
or
z equal to z naught.
z equal to z naught. Okay,
Hmm,
okay,
hmm. That's the location of the singularity. Can I move on?
sure, sure, sure.
Okay, so L, like I forgot to mention, L is the ADS radius for this. So we evaluated the action complexity, and it exhibits certain UV divergent pieces. Delta is there, it's a UV cutoff. Uh, and this first term, it has a leading UV divergence structure, which is consistent with the 2D CFT, because and delta X as a cutoff. The leading piece uh, is the one coming from the pure ADS background. Recall that it is the ADS, yeah, pure ADS background, and the this finite piece, this correction term, it contributes negatively for all values of parameter alpha. So this is the range of parameter alpha. It lies between 0 and 1. So for all values of alpha, so you have this second term, which is a finite piece, but it's a negative piece. So we see that this action complexity is consistently lower than the empty ADS on the whole allowed range of this Kazner exponent. So this is a clear indication that perhaps the action complexity criteria is consistent with the Gupser criteria, and because it rules out the Kazner geometry. Recall the Gupser criteria also rules out this geometry because this time-like version does not exist, does not appear as an exact solution to ADS sugar equation, but it is a weak rotated form of that, which is not there in the ADS sugar equations. But this just occurs at the holographic theories, condensed matter theories. So yeah, we find a match, like an agreement between the Gupser criteria as well as the action complexity criteria. It's time to look at what the volume complexity has to tell us about this. So volume complexity also has this leading UV divergence structure, which is quadratic. It is in agreement with what a 2D CFT would have. And because recall, this is 4 dimensions, the CFT will have 3 dimensions and its spatial volume will have 2 dimensions. So it is consistent with CFT2 result. First term is again the ADS result, and there is a second finite piece which is different from what you have in the case of the action complexity. Volume complexity piece is different, but this complexity piece, it changes sign at alpha equal to 2/3. So only in the range when alpha is less than 2/3, this whole piece is negative. There's a negative contribution, and it agrees with our Gupsa criteria as well as the action complexity criteria only in this restricted range. But in the range when alpha is greater than 2/3 and less than 1, this term is positive. Somehow that time-like singularity, geometry of that time-like singularity, the corresponding boundary state complexity will be greater. So it is not in sync with the Gupsa criteria. So we can, so we see that CV is not so on this full interval of this Kazner exponent, this alpha. The last system we look at, so after getting this encouraging result for the action complexity, so we turn our attention towards a very interesting case this time, of a geometry that undergoes a phase transition. This undergoes a phase transition as a part of as a function of this parameter alpha. It undergoes a phase transition from an allowed phase of geometry to the disallowed phase according to the Gupsa criteria. So Gupta criteria partly allows this geometry and partly disallows it, depending upon the value of this exponent alpha, right? And yeah, and we try to see whether our action complexity criteria is also able to capture this phase transition or not. And also on top of that, also able to reproduce any agreement with the Gupta criteria or not. So this Einstein scalar system is in asymptotically ADS space-time. It contains time-like singularities. The geometry is described by this metric, and as we dial this exponent alpha from values below, from the values which are below 1 upon under root 3 to greater than 1 upon under root 3, what happens is that this naked time-like singularity, it goes from disallowed phase to the allowed phase. Because in the range when alpha is less than 1 upon under root 3, the Gupser criteria is violated, because this singular geometry cannot be obtained as the limit, as an extremal limit of any finite temperature geometry in the full string theory. So when we evaluated the volume complexity, we found that volume complexity, it totally fails to register the phase transition. Therefore, we rule it out as not being a sensitive or a reliable probe for treating the time-like singularities. And this we have also seen in the previous case as well. But action complexity, uh, on the other hand, the action complexity is given by this expression where we treat this lambda as a bulk IR cutoff. And epsilon here is a bulk UV cutoff. We see that the leading action piece here, it scales in the cutoff consistent with the pure ADS result, that is lambda square, like, and this has been consistently for all the other cases. And in the allowed case, in the allowed range when delta is greater than 1 upon under root 3, the action complexity, this term is 0. Because when delta is greater than 1 upon under root 3, I'm taking this epsilon to 0 because it's a bulk UV cutoff. So this term goes away. This is not contributing. This is the subleading term. So this subleading term is positive, manifestly positive for all values of delta, which is, yeah, for all values of allowed values of delta. So you see that the action complexity registers a value greater than the pure ADS result for when alpha is greater than 1 upon under root 3. But what happens when sorry, delta is sorry, I'm sure, sorry, I made a mistake here. Delta is alpha. I should have alpha here. I'm calling alpha delta. Delta is not a cutoff. Cutoff is lambda, like I mentioned. Lambda is a IR cutoff, bulk IR cutoff. Delta is this exponent. So I made a mistake, like it should be alpha, not delta. So what happens as I take my delta to be less than 1 upon under root 3, what happens is that, first of all, this term flips sign, and the exponential also flip sign, bringing epsilon in the denominator, and it blows up as I remove this regulator. So what happens is that this action complexity is consistently negative infinity. It is unbounded negative. So this is a very in physical result in the range, in the disallowed range of the geometry. So we see that the action complexity is a sensitive probe detecting the phase transition about this value of alpha, and it is also able consistently able to agree with the Gupse criteria, and it does it we can hope that it may provide an alternative diagnostic to the time-like singularities occurring in this bottom-up approaches, apart from the Gupse criteria, which is operationally difficult to implement. So yeah, so with this I'm concluding. So we see in this work that the time-like naked singularities, naked singular solutions, they can have less complexity, or they can be more complex than the empty ADS geometry. So having a less complex singular geometries as compared to an empty ADS background, it is a sign of sickness for the singular geometry. And that is true for the case of the action complexity, which we consistently found for these three examples. And we have also seen that volume complexity is not a reliable tool to probe the time-like singularities, but action complexity criteria, which we formulated, it always is in sync with the Gupse criteria for all the test cases, these three. But the sample space we treated for the time-like singularities, which we explored, is not enough to rule the CA as a universal probe. Therefore, we need to conduct a very exhaustive survey for other geometries containing time-like singularities in the bulk in our future works. So with this, I thank you all for your attention, and I can take questions now.
So, what do you mean by negative complexity? I don't understand it.
By negative yeah, so that is unphysical, like there should not be, and there's no meaning to negative complexity, it cannot be negative. So that is again a sign of unphysical result, which you it doesn't make sense, like it is unphysical. There's nothing like negative complexity, because the way it is defined, by its very definition, it just counts the difficulty, the number of steps or the number of unitary gates you are applying to go from A to B, state A to state B. So it cannot be negative. Yeah.
Okay, right.
Yeah.
Hi Gaurav, can I ask a question?
Yeah, why not?
Yeah, so in the Casnet geometry case, you showed that the volume complexity becomes unreliable at some alpha value, which is 2 over
Right.
3.
Yeah.
So,
Yeah.
is there any understanding of maybe what is happening physically at that parameter value? Is
Well, okay, but until this point we were at dark, like until this point, but when we looked at this geometry, we consistently found that volume complexity, it fails to register the phase transition. So like I said here, it's not a reliable probe, and we rule it out. So we can go backwards, and we see that we can implement the same chain of thought, which tells us that this is not a reliable probe. So it is nonsense whatever it tells
yeah, I'm not completely sure because I mean, it's still an interesting question to consider that in what scenarios the volume complexity can also give you reliable results, and if
you. Yeah.
uh, there is certain range, it will be interesting to understand that.
Right,
For
that's true. That's
example,
why when I concluded,
I
right,
mean, yeah.
maybe what we thought is that perhaps it's not a good probe for the time-like singularity. We know that it is a good probe for space-like singularities or other space times. even the cosmological singularities, it like the CV and CA consistently they agree, but that is not true for the time-like cases. And like you said, yeah, we have to probe. Like I mentioned, like we have not explored all the sample space of the possible time-like singularities, and we'll be able to comment on that more, with more certainty after we have conducted that exhaustive survey to check, like under some test cases, how CV behaves. But until now, in these three test cases, only CA comes out and as a true probe, and CV was a bit nonsensical. It gave unphysical results, not unphysical results, but it didn't agree. So we just ruled it out. We are ignoring it. Like, yeah,
Okay.
that's all I can right now.
Okay. Thanks.
Yeah, yeah, welcome.
Hello.
Hello.
So I just want to ask that the graph that you showed in the starting, that complexity increased and remain constant and then it decreases. So
Yes.
so is it also true in general, or it is specific to this ADS case? That
Right. Oh, no, no. This is true in general. Like complexity linearly increases and it hits this plateau region. But that is true for a quantum mechanical system, because for a quantum mechanical systems, you have something called a Poincare recurrence time, which I didn't mention here. So after it stays there for a very, very long time, which is doubly exponential in the number of degrees of freedom, and it comes back. So that's true for the quantum systems. For classical system, we are just interested in this curve because this is a very, 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 very long time scale. This is a time scale as which ERB evolves and goes very, very close to the singularity. So this is the physical time scale which we are interested, or like which gives us some universal evolution characteristics in this range. But yeah, this is true for quantum mechanical
yeah.
systems, because your Hilbert space will have many exponentially complex states, and those are exponentially numbers. So it traces out those states. Your system, it goes through all those states and stays there, excruciating through all the states. So it stays there for most of the time.
Okay, so it is. I mean, it is true for any state like that.
In a
Complexity.
quantum mechanical system,
So okay,
quantum
so in
mechanical
quantum
system.
mechanics, complexity of any state initially increases, and then at very large time, exponential time, it start decreasing again. Right.
Yeah, it comes back to
Okay.
after
Yeah.
something called a Poincare recurrence time.
Oh. Okay. Right. Okay. Okay.
So, if no more questions are there, we can thank the speaker. So, thank you, Gaurav. Thank you so
Thank you
much.
so
Yeah.
much for your attention. Yeah, thanks everybody. So can I log out now?
Yeah,
All
yeah,
right.
sure. Bye.
Okay. Thank you. Bye.